2008, when the world first heard about CERN's ambitious project to launch the Large Hadron Collider, many people were gripped by fear and apprehension. After all, rumors had it that this massive particle accelerator might create a microscopic black hole that could swallow Earth itself. The world held its breath in anticipation, and some even filed lawsuits to halt the LHC's launch. In this video, we'll explore what became of these fears after the collider's launch. Was there a real risk of creating a black hole on our planet? And if a micro black hole really appeared, what threats would it pose to our world? What would happen to the solar system if a bigger black hole entered from outside? What are these space monsters capable of? Could they serve as portals to other universes, or are they merely deadly formations that only destroy and devour? How long do they last? How big can black holes be? Giant black holes. Now guys, can you imagine something incredible? A black hole? This phenomenon is so mysterious and enigmatic that it's not fully understood by even the most brilliant minds of our time. A black hole is not merely a region of space, it's an area with density going to infinity, where the gravitational attraction is so powerful that even light itself cannot escape. Black holes often form when a star depletes its thermonuclear fuel and explodes as a supernova. The inner layers of the star no longer generate enough pressure to balance the outer layers, causing the star to collapse into itself. This process generates extreme energy, producing a flash visible across the entire galaxy or even beyond. At the same time, the matter inside reaches extreme density. Sometimes a neutron star forms as a result of such compression. The matter's density in a neutron star is so high that a teaspoon of neutron star matter would weigh billions of tons here on Earth, and an even greater density is required for a black hole to emerge from a supernova. A formed black hole is something beyond our comprehension. These objects have no surface, yet they can rotate sometimes at an unimaginable speed. Black holes distort space and even time itself. A small black hole can tear apart and devour a massive star. Whatever enters a black hole can never, under any circumstances, escape it. In 2008, the launch of the Large Hadron Collider raised concerns in the global media due to fears of a black hole appearing on Earth. How so? It's all about the massive amounts of energy the collider operates with and the incredible states of matter that arise during the experiments. The main task of the Large Hadron Collider is to reliably detect any deviations from the standard model, a set of theories that form the modern understanding of fundamental particles and interactions. To do this, we need to delve deeper into elementary particles than ever before, and that's why the LHC requires such monstrous energy. However, these concerns proved to be unfounded, and the collider has been operating for over 15 years. As for black holes, we probably don't need to worry about their formation on Earth. Nonetheless, it's intriguing to consider whether it's even possible for a black hole to appear on Earth. Let's figure it out. In fact, any object, including you and me and everything around us, could potentially become a black hole. To achieve this, we must compress it into its gravitational radius, the threshold where any object turns into a black hole. Such a radius can be calculated for any space object in the universe. Interestingly, the gravitational radius of regular objects is minuscule compared to their actual size. For Earth, it's only 0.887 centimeters, or 0.35 inches. Now, just think about this. To turn the Earth into a black hole, one would need to compress it to the size of a peanut. And to create a micro black hole in a collider that would even be remotely dangerous, you would have to gather in one spot the mass comparable to the Moon. Humanity is far from having such capabilities, but let's do a thought experiment anyway. Picture a peanut-sized black hole appearing on Earth, regardless of its origin. Well, let's say future scientists create it in a super collider. What would happen next? To put it mildly, nothing good would come of it. One likely scenario is that the black hole would immediately dive into the depths of our planet and move towards its core roughly at the speed of a free-falling object. It would absorb surrounding matter on its way, but this wouldn't be the main issue compared to the monstrous gravitational turbulence created by the combined gravity of the black hole and the collapsing planet. our planet would be quickly torn apart and then the black hole would slowly devour its remains. Over time, this system might even stabilize, forming something like a donut, similar to Saturn's rings but with an invisible small black hole in the middle instead of a planet. Now let's push our curiosity and imagination further. Imagine a genuine non-artificial and non-microscopic black hole appearing in our solar system. You may wonder, how is this possible? The answer lies in the hypothesis of wandering black holes. Although the probability of such a terrifying encounter is extremely low, it's not zero. So what would happen to the solar system if a wandering black hole entered it? The outcome would depend on several factors: the mass of the black hole, its trajectory and velocity. If it's a typical black hole formed as a result of a supernova explosion, we're in for trouble, even if it enters the periphery of our solar system. Suppose it appears near Jupiter, it would quickly tear apart and swallow the gas giant, becoming the center of the solar system. After all, it would be much more massive than the Sun. It's frightening to imagine the impact on the orbits of the planets and the Sun itself. The current harmony and synchronized motion would be abruptly put out of balance in the most chaotic way. And what about Earth? Would it burn up, passing too close to the Sun, or collide with Mars, or perhaps be flung out into deep space? All scenarios are dreadful, and a positive outcome is nearly impossible. Alright, we already know about black holes' superpower to inevitably absorb any matter once and for all. But what comes next? What's inside black holes? What happens to the matter once it gets in? There is no definitive answer yet, and there may not be one for a very long time. The issue isn't just the distances spanning tens of thousands of light years. The problem also lies in the fact that any research apparatus sent there would simply disappear without a trace. Not only wouldn't it return, but it also wouldn't be able to transmit any signal, not even a single quantum. And of course, no one would ever send a human into a black hole. This will likely always remain a subject of science fiction and thought experiments. But if that's the case, why not do such an experiment right now? What would a person feel if they fell into a black hole? As a person approaches the black hole, their view would become increasingly darker. At a certain point, the traveler would reach the photon sphere. This is a unique orbit where the photons of light aren't yet falling into the black hole, but they also cannot escape its gravitational embrace, thus moving in a circle. If they could linger at the level of the photon sphere, the poor thing falling into the black hole would be shocked to see their own back of the head. This is because photons of light reflected from the back of their head would orbit the black hole and fly straight into the traveler's eyes. Next is the event horizon, the no turning back point. Our hero moves towards singularity, a place in the center of the black hole where the density of matter becomes infinite, and even physics changes so much that time and space become something completely different. Looking back, the traveler would see that the universe behind them seems to contract, eventually turning into a point. That's not all to it. At some point, the person would start to feel pain. As the astronaut gets closer to the black hole's center, tidal forces will increasingly affect their body. For example, if a person fell feet first, their legs would be attracted to the center much more strongly than their head. The body would literally begin to stretch. This effect would be uniform throughout the body. With the body stretching like spaghetti, this process is actually quite creepy. There even has been coined a scientific term for it: spaghettification. The unfortunate astronaut would die long before reaching singularity. In rare types of black holes, there would be a chance to live until that moment and personally feel what it means to enter the center of a black hole. Most likely, this would be the last thing such an experimenter would experience. No one really knows what singularity is and how it would affect the astronaut's body. It would probably be destroyed in the most brutal way, torn apart and then broken down into molecules. However, there are hypotheses that black holes could actually serve as portals in space and time. Interestingly, this hypothesis fits well within the laws of physics and doesn't directly contradict them. We'll discuss this fascinating hypothesis in more detail later on. One thing's for sure, a black hole is an unexplored, dangerous, and most likely deadly place. But if black holes are like super predators of the universe, this prompts an interesting question. Do black holes have anything to fear? And are they eternal? Black holes can exist for billions and billions of years. Their life cycle depends on their mass and a process called Hawking radiation. This intriguing phenomenon not only provides no answers to questions, but on the contrary, raises a bunch of new ones. Until 1974, scientists believed that black holes couldn't emit anything due to their enormous gravity. However, it was Hawking who showed that black holes could emit radiation. This is a very peculiar process where the black hole loses mass due to quantum phenomena and its boundary. As a result of these phenomena, virtual particles and their antiparticles appear near the black hole's boundary. In simple terms, sometimes one particle falls into the black hole and the other one escapes into space. This leads to the loss of the black hole's mass and generates the above-mentioned radiation. Currently, we're very far from getting any experimental evidence, but the scientific community is confident in the existence of Hawking radiation. Thus, having colossal masses, supermassive black holes can exist for an incredibly long time, for quadrillions of years. They are among the longest-lived objects in the universe. But they're not eternal either. Let's go back to the amazing idea that black holes might actually be portals to other areas of space or even other universes. Indeed, there's a hypothesis that black holes may create so-called wormholes that one could use to travel faster than the speed of light. This is not due to the violation of the laws of physics, but rather the multidimensionality of the universe. To understand this principle, let's take the most vivid and well-known example. Imagine a sheet of paper with 2 points on the opposite ends. To move from one point to the other, one would have to go across the entire sheet. But if you fold the sheet correctly, these 2 points will be very close together, almost intersecting. All that's left to do is some trivial stuff such as learning to skillfully bend the fabric of space. But we know who is the go guy here. That's right, black holes are excellent space-time distortionists. And the probability that at least some black holes are capable of forming such wormholes can't be ruled out. Now, we bet the theory about portals to parallel worlds doesn't seem too out there after all. The gravity of black holes is immense and is often concentrated in an extremely small area of space, which leads to astonishing effects that we've already discussed. It's a common belief that black holes are the main reason for the spiral shape of galaxies. The idea is that massive black holes attract and hold matter around them due to their gravity. Can you imagine this gravitational force capable of holding entire galaxies in orbit? But of course, this is not the case. Even the most massive black holes loses its power at such gigantic distances. Something else causes galaxies to be spiral. However, this doesn't negate the fact that there is a massive black hole at the center of almost every galaxy. And our galaxy is no exception. There is also a supermassive black hole at the center of our Milky Way. It lies very far away, 26,000 light-years from the solar system, in the Sagittarius constellation. It has a whimsical name of Sagittarius A. Luckily, even being supermassive, it doesn't pose any danger to us. By the way, we constantly talk about how massive black holes are. How much matter have these monsters managed to absorb so far? Maybe they already weigh more than all the other matter in the universe combined. Actually, no, not yet. But it's not a small amount either. According to recent research, approximately 1% of all regular baryonic matter is contained in stellar mass black holes. In scientific terms, this means that in every cubic megaparsec of space, a megaparsec equals 1 million parsecs or 3.26 million light-years. In our universe, there are roughly 50 million solar mass black holes or even heavier. To give you an idea of the immense sizes they can reach, let's discuss 3 known supermassive black holes. Imagine a vast elliptical galaxy with a real space furnace at its center. Meet Messier 87 with the core that generates incredibly powerful radiation encompassing the entire galaxy and extending far beyond its boundaries. But here's an interesting fact. This radiation stream is not just a random phenomenon. In fact, it is the result of a supermassive black hole located at the galaxy center, making its core so active. how does it work? The supermassive black hole absorbs vast amounts of matter that orbit around it. Spinning at tremendous speeds, the matter heats up to unimaginably high temperatures. These processes generate a powerful stream of radiation, including gamma and X-ray emissions. But there's more. In addition to radiation, the black hole generates a relativistic jet, a stream of plasma ejected from the galaxy's core. It's called relativistic because the matter it contains moves at speeds closer to the speed of light. The jet stretches over an enormous distance of at least 4,900 light-years. The mass of Messier 87 black hole is estimated to be around 6.5 billion solar masses. TON 618 is something monstrous even by space standards. Presumably, the galaxy center hides a gigantic black hole, devouring massive clouds of hot gas, forming an accretion disk around itself. Over billions of years, this colossal reactor has accumulated a vast amount of matter, gradually increasing its mass to 66 billion times greater than the mass of the Sun. This phenomenon is so incredibly powerful and gigantic that scientists coined a special term to denote it: a quasar, from the words quasi-stellar and radio source. Quasars are considered the deadliest objects in the universe. At the same time, they're fascinating. After all, a quasar shines so brightly that its light eclipses the light of the entire galaxy where it's located. And now, thanks to the latest space research technology, we can observe this awe-inspiring performance, even though it is a staggering 10.37 billion light-years away. Astonishingly, this cosmic monster is 140 trillion times more luminous than our beloved Sun. Our biggest and brightest space chart ends up with a truly colossal monster discovered relatively recently during one of the missions of the Sloan Digital Sky Service (SDSS) program. We are talking about another ultra-bright quasar. Presumably, it lies about 16 to 17 billion light-years away from us, and may be around 10 billion years old. In terms of luminosity, this awe-inspiring space object is inferior to TON 618 and has 56 trillion times the luminosity of the Sun. But its mass is an absolute record breaker. Most likely, it weighs about 196 billion solar masses. Gigantic black holes are undoubtedly extremely dangerous and even deadly phenomena in our universe. They defy physics itself, not to mention what they can do to regular matter. But for the most part, they are at a safe distance from us, and we can calmly observe and study them, comprehending more and more amazing secrets of the universe.